Okay, we're back. So, again, our challenge is to find a brick that kind of matches these in color, strength, functional performance, and preferably the amount of smudged mud and spilled quickcrete dust, so that they all kind of blend and flow naturally. So the most important part of any engineering project here at Plan B Engineering is getting our requirements right. You can't build the right system if you don't start out with the right requirements. Okay, so I'm going to show you how to do that. So here you have a hole. You've already tried a COTS product, and if you're not familiar with that acronym, COTS is commercial off the shelf. That's that would be this, right? So we already tried the COTS product, and it didn't fit. And I'm not going to go back and recreate that. Hopefully you'll take my word for it. But this size brick didn't fit this size hole. So that's the problem that we're trying to solve. And so the first thing we got to do is understand, well, how big is this hole? And so what you need, it'd be better if we if we had a laser. A laser could measure from here to here, and we could get it down to the sub nanometer level in accuracy. And for a lot of the things I do at my real job, which is build spaceships, that's very important. But for a do-it-yourself project like this, we have just a little bit more tolerance and margin, and if we don't get this quite right, I think chances are still reasonably good that there will be no loss of life, and hopefully no loss of mission either, but I don't think we're risking the crew's safety here. Okay, so what we have instead is a much less precise, much less expensive tool here to come up with our requirements. And so what I've got here is a tape measure. And so I need to measure the smallest point here. I'm going to say 3 1/4, and the reason I'm saying that is because I have no interest in fetching my reading glasses. I can see that 3, and I can see the 4, so it's something between 3 and 4, and so we'll take note of that for our requirements. Then we need to know how long it is. So take another measure, and I'm going to say 6-ish for that, and then we need to know how deep it is, and I'm going to say that. Oh, I'm not. I need a better cameraman. So I'm going to say that's about 2. Okay, and so that's our specifications. Those are the dimensions, and then we also had the functional performance requirements that I talked about, and the aesthetic requirements, trying to match the form, fit, and function of these COTS garden bricks. So now I'm going to go over to our fabrication facility. All right, here's the fabrication facility, which has a lot of spare parts. Some of them are kind of dirty, but this fabrication facility is a multi-purpose facility. This is also where we polish our rocks. To do that, we use this handy dandy power washer, and we do that over at the edge so the water goes off. But when our facility isn't in the middle of a huge project like this, and the aisles are a little clearer, this facility doubles as the basketball court. You can see from the seating configuration that here at Plan B Engineering, the enjoyment of our fans is top priority. Their safety is somewhere below top priority. Okay. Okay, so here's our fabrication facility, and we have some high-tech tools. We made some very, very precise measurements, so now we just need to cut to those. And so you know, and I've already done this, so I'm going to show you the finished product here in a minute, but here's how we do it. What we do is we start with a COTS product that's as close to the form and function and fit of our end product. And so you can see here, this is one, I would say right off the skid, but because I had a whole pile of these left over from another project, once I realized I couldn't buy the precise size from the local Home Depot, I just dejectively drove home without purchasing anything. I did get some nachos and a Dr. Pepper on the way home, but that's another story. We put the raw materials in our workspace, and then we take our tools, and for this kind of precision engineering, we have, you know, some choices. We typically will always use this. What this is a chisel, and so, you know, we put this about where we measured to, and let's see, what was it we had? I think the problem was that our tape measure had inches, and being a aerospace engineer, my brain only thinks in centimeters or millimeters, or you know, whatever prefix you want to put on a meter. But you know, we can get over that. So here's our chisel, and then we actually have a choice depending on, you know, how precise we want to be. You know, if we want you know, to really precisely match our hole, we have this device to use in conjunction with the chisel. If we oh shoot, there's another copyright fee. Oh shoot, we have this device, and by the time, you know, we edit that, we will be free of any kind of copyright violations, or I don't even know if that's a copy. Anyway, if we're okay with a little bit less precise end product, but we want to move just a little bit faster, then we have this device. This one is heavier, but, you know, less accurate. What we do is we place the chisel at the precise measured distance, you know, from the edge, and then we strike said chisel with this device. Do that, you know, all along here until we've got a line, and then we kind of keep doing it again, and we keep, you know, we use this to scrape out the inside, and then, you know, once we get the fracture dug deep enough, we run a program called FlawGrow, which is a program that predicts how fractures will spread. It's a very common tool that we use in the human spaceflight design, you know, programs, because, you know, it's really hard to predict how a crack's going to go, but you know, we use that program, and then when we feel like, you know, the crack is deep enough and straight enough that the program predicts that you know, we can provide some additional force, and we really have a high likelihood that the crack's going to propagate in the direction that we want, which is, of course, straight down. Then we remove this piece of the apparatus, and we go just with this one, and we use a little more force, and then we come up with a final product, which I did earlier. You know, once I have a subscriber, I assume I'll have a, you know, a substantial budget, and then I'll get a camera person, and then I could actually show you, you know, how I got this busted thumb by showing you, you know, how to actually work the apparatus. So anyway, now let's just check, because in every good engineering project, you build your system, and then you have to verify that your system meets your requirements, and so that's the phase that we are at now. And so what we have to do is measure this. So let's see, I'm not exactly sure we got the right orientation here, but this is 2 inches across, which is 5.08 centimeters. It's good when you have round numbers like that, because then my my little brain doesn't have to work as hard to do my mental conversions. So 2 inches across, and I can't really remember, but I know that one of the dimensions we had was 2, and so let's see how tall it is. You see that's between 3 and 4, and yeah, that matches one of our requirements. And let's see, I guess this is a 3-dimensional object, right? Oh my. And that one is right at 4. Maybe that matches our other one. So great. I would say that we have verified that our system meets its requirements. So now the next and most exciting phase in this sub-project of our do-it-yourself pond project is we're going to do the installation. So I'll be right back.